Okay, there are two phases to the cardiac cycle, okay? And what is it that makes that characteristic sound should you be having a stethoscope and listening to someone's heartbeat? What is it that causes that? It's called that dub-dub or lub-dub or however you want to call it. How or what is it that's making that noise? Right. So when we talk about the two phases of that cardiac cycle, when them valves are slamming shut, okay, what are your two cardiac phases? Systole and dystole is your two cardiac phases, but and you're right, but which ones which? When the atria contract, of course the ventricles are relaxing. So when that happens, which phase is that? Is that dystole or systole? It is systole. I'm going to say, are you sure? But yeah, you said it. Was that confidence or no?
I roughly know.
Okay. So when systole is occurring, your atria are contracting, okay? So you can presume, okay, when systole is taking place, atria contracting, what valves are open? Now you have to remember what separates the ventricles from the atria. Okay, it's not blood vessels, it separates the actual chambers. Okay, and the reason in these questions possibly seem confusing, but if you can navigate through there, you have a very good understanding then of the human heart. So what we mean by that is when systole is taking place, these two chambers are contracting at the same time. So what valves would then be open? Systole occurs, atria fire, these valves open. So it's what two valves separate the chambers, the top from the bottom? That's one, and bicuspid, okay? So then on the left side of the heart, is that the bicuspid valve or the tricuspid valve? Tricuspid valve. On the left side. It is, or the mitral valve. Then on the right side is your tricuspid valve. So then what you're actually hearing is your semilunar valves are slamming shut, okay? Because when systole takes place, that blood has to be able to flow through and it gets down into the ventricles, okay? So then when that happens, those are slamming shut. That's the lub. Then in dystole then, okay, the semilunar valves open up because the ventricles are then contracting, and then which two valves are slamming shut? If it's not the semilunar valves, those are open. Which two valves are then going shutting? It's again what separates the top from the bottom of the heart, because these valves are now closed to keep blood from going back into the atria. Tricuspid and bicuspid, that's right, okay? So I don't know if you've ever, I'm not saying that you'd question it or wonder why. Why is it that if the pressure is much, much higher in the left ventricle, why is that a bicuspid valve, and between the right ventricle and right atria, why is that a tricuspid valve? I don't know if you've ever questioned that. I suppose you could say it's just the way the man upstairs designed us. I suppose you could say that. But for me, when I'm thinking about that, okay, those fibers that are attached to those valves then, okay, when you're looking at a cross section here, okay, again, here's your heart here. Again, it's kind of offset a little bit because this side's bigger than that, okay? We know that with your right atria and right ventricle then, okay, this is where your tricuspid valve is located. So when we see a top portion of that, okay, you would picture, since that kind of looks like a circle, I don't know how accurate that is. Does that look like 120 degrees each? Sure? Okay. So to me, I've always looked at that. There's a potential for a weak spot where all three of these are coming together right here. When you're looking at the left ventricle and, oops, it's supposed to be a V, and left atria, okay, then that's just a straight line going across. It's much stronger here than here. There's more opportunity for a weak spot. Now, how accurate that is, I really don't know. There's maybe what a cardiologist or maybe your personal physician or doctor said, oh, no, that's not right. But that's just how I've always thought of that there's just more of a chance for a seepage. And there typically is. That's where heart valves typically do need to be replaced, is in between these two chambers. And should there not be an opportunity, well, go to the slaughterhouse and get a pig's heart. Take the tricuspid valve out of there and put it into humans. And that's pretty routine to actually do that. Okay, so moving forward then, okay. And we'll, I'm not saying we'll keep this short, but we don't have a whole lot to go through on account of, are you thinking how crazy it is that you're in the low 20s for school days left, or is it hurrah, hurrah? Then for seniors, it's even less than that. Definitely hurrah, hurrah. Okay, so this again was your systole and distole that we had talked about, okay? Like you had correctly said, the ventricles are relaxing in systole, and then in distole, the atria are relaxing, okay? So what happens as we move forward, we know that anything carrying blood away from the heart is going to be an artery. It doesn't matter if it's red or if it's blue. It's going away, it's going to be an artery. So again, there's really no clear-cut definition between an artery and an arterial. It's where we're saying, okay, an artery has to be 3/4 of an inch in diameter. If it's going to be classified as an arterial, it has to be half that, it has to be 3/8 of an inch. No, to my knowledge, there's really no definition just between the sizes of these. It's just a smaller branch is one way to look at it. And one of the questions that you were asking earlier, to supply blood to the legs, that abdominal aorta has to split, and it does, okay? And it's called the iliac region, okay? And in that iliac region, you have a left and a right iliac. Those are certainly still very large, so those are not called the iliac arterioles. They're still iliac arteries. Even when you get further into the upper thigh, okay? So your hamstring area and your quadriceps area, okay? Those are the muscles. What's the bone in that vicinity, do you think? Okay, the femur, okay? So then you have what's called a femoral artery, and branching off of the femoral artery is the deep femoral artery. And at any time, if it's unfortunate enough, any sort of trauma, if these get cut, or even these, for some odd reason, why is that? I'm not saying that person is in trouble, but as far as bleeding internally, Why is that so much of a problem, more so than veins would be? Yes, for every time that heart is contracting, the pressure in here is so high that having that ability to clot is just going to be that much more difficult. Okay? So then, once you get past the arterial, what's your smallest blood vessel then? I said vessel. I didn't say artery. I didn't say vein. I said smallest vessel. Yeah, it's going to be your capillary bed. Okay? I would think it would talk about that eventually. Oh, right there. Okay. Did I go too far? Okay, here we go. Should a primitive reaction in the brain be that we really need to increase the blood pressure? Okay. And in order to do that, this structure would do that. Okay. Because when you think of any type of vessel, okay, they're circular in structure. No surprise there. And one way that you can visualize that, of course, is looking at this, not vein, but this artery, because it's carrying blood away from the heart. This is your pulmonary artery here, which then goes to the left lung, and then behind the aorta, splits here, going to the right lung. Okay? But what happens is this smooth muscle, do you have conscious control of that structure if it's smooth muscle? No, you are consciously turning your head, you're consciously looking up, you're consciously moving your hand and your fingers in your writing. That is, of course, voluntary muscle. This, however, is involuntary, okay? Because you do not have conscious control over that. And one way to visualize this, how blood pressure is increased, is you're going to visit grandma or grandpa, if you still have them. When I was your age, my grandparents were almost gone and had passed away. But for our purposes, you go to visit grandma, and one of her flower beds is 70 feet from the side of the house, okay, or wherever her garden hose hooks up. That garden hose is only 30 feet, okay? But you unwrap that as far as you can, you turn that garden hose on. I guess that's a little drastic to make up 40 feet. It's 30 feet, and the garden is 40 feet away. So you got your 30-foot hose, you got 10 feet to make up. Well, as that water is coming through that garden hose, how do you get that to go an extra 10 feet? You have to increase the pressure. You can't increase the flow. That is going through at a fixed rate, but you can change the pressure in that hose. And how would you go about doing that? Yeah, when you put your thumb over the end of that garden hose, the flow rate is still the same. The velocity is really going to shoot up. And of course, the pressure is going to go up. So what you're doing is you are constricting the end where that water is flowing through. The human body works very similarly. This smooth muscle will start to constrict. And then what does that do to the velocity? As just like the end of putting your thumb on that garden hose, what does that do to the velocity? Does it go up or down? It goes up. What does the pressure do? It goes up as well. So that is one way that the body will compensate for increasing blood pressure. It could be for various reasons. And this is just one way that the brain will do this. Now, where does that take place in the brain? Probably somewhere, maybe back in your cerebral cortex, but probably the best answer for that would be in your brain stem, just where all your vital reflexes are in that water boy medulla oblongata, where Mama's wrong again. Poor Mama, she's no. We're not going to go into that. I just think that segment's so funny. Oh, the old medulla oblongata. Okay, so I want to talk about this, and then that, and then tomorrow we'll go ahead and move on to these. Okay. Because one of the things we see here, okay, of course, this is on the far inside. So it's a thin layer of this connective tissue that will, okay, have cells reproduce and connect and make new blood vessels. How do we know that happens? When we saw that video about a heart attack, it wasn't Robert, it was his name, that suffered that heart attack in the video. Say that again? John, yes. John was his name. Okay? So in his heart, okay, these coronary arteries, which would also have on the very outside, would have this tunica externa, that these cells would start to reproduce and connect and make new blood vessels. Now, is that process fairly quick, or is that what would have to take place over maybe 3 to 4 days? Yeah, it's going to take a little bit of time to do that, okay? But it's still possible that these cells are able to divide and make new blood vessels, but it's just not efficient enough, unfortunately, for John, who then had a blockage in his heart and then caused a heart attack. Now, that blockage then was due to lots of cholesterol, okay? And then those globulates just start to stick together and forms a plaque. And then, unfortunately, just think of this when you a lot of, I don't want to say moisture, the ability to, when you put your hand on that, should you do that, it actually feels kind of sticky because that's lymph tissue. Well, when that plaque breaks, same type of concept, then blood cells flowing through the heart are going to start sticking to that plaque. And then the more clots that you have in there, it totally shuts that artery down, that coronary artery. So then wherever that takes place, if it's right here where my finger is, anything beyond that is just not going to get any nutrients or, more importantly, oxygen. Okay. Last thing for today, then we'll be done. When your muscles constrict, okay, think of, or even your pupils, that's probably a better way of looking at that. When you're looking at something bright light, do your pupils get bigger or smaller when you're looking in bright light? They get much, much smaller. So then when someone's pupils are dilated, then the iris, which is actually a type of smooth muscle that lets light in. So if there's really bright light, the iris constricts and lets very little. The pupils are really, really small. Then if there's low light, your pupils or your iris dilates and your pupils become very, very large. So the way it looks as we proceed forward, you have your Smarter Balance testing tomorrow, so your vocabulary evaluation then will be on Thursday. Then we'll see once where we're at. And then don't forget, start looking at your blood vessels your chambers of your heart, your vessels in the heart, what's leaving the heart, what's in which circuit, pulmonary or systemic circuit, and then we'll start going through these different branches, okay? Now, when we're talking about what's leaving the heart, okay, now this is not easy. As you're going through this aorta, we said you got this brachiocephalic trunk, a left common carotid, and then a left subclavian, and then that branches into further, if you want to call it tributaries or exits on the interstate. Sometimes that's a good way to look at it. As you're going south towards Sioux Falls, Interstate 29 is your aorta, whether it is your thoracic aorta or your abdominal type. Then every time you get off on an exit, the first exit south is which one? Starts with a T, ends in a T. The Trent exit. I suppose you could say Chester as well. Then the next exit after that, the best one, the Del Rapids exit. That's right. Okay. Then after Del Rapids would be Baltic. Then after Baltic, I believe, is Lyons and Crooks. Then after that is Renner. Maybe that's Renner's part of that Crooks exit. Then the next one would probably be your Interstate 90 interchange. But every time you get off on an exit, that's kind of like a tributary leading off of the aorta. Okay, that's all I have. We'll catch up to you next time.